Earth Systems 3209. Unit 4, the forces within Earth. This unit you can find referenced in the textbook in Chapters 4, Chapter 15, Chapter 16, and Chapter 19. You can also find references in Appendix A and B of the curriculum guide. Unit 4, Topic 4.5. We'll look at locating an earthquake epicenter. This lesson will focus on describing how seismograph records can be used to locate the epicenter of an earthquake. When locating the epicenter of an earthquake, the source of an earthquake is called a focus, which is an exact location within Earth where seismic waves are generated by sudden release of stored energy. The epicenter is the point on the Earth's surface directly above the focus. This is the location that scientists calculate. The focus is directly below. However, scientists cannot determine its depth. They can only locate the position on the Earth's surface directly above the focus. To locate the position of an earthquake epicenter, we need a seismogram reading from at least 3 different seismograph stations, and a travel time graph which shows the speed of both P waves and S waves. We can see information in the textbook on pages 447 to 448. Let's look at locating the epicenter by looking at seismogram readings. Step 1. 3 seismogram records are needed in order to locate the epicenter of an earthquake. First, we find the difference in arrival time between the P wave and the S wave. To do this, refer to each of the 3 seismogram readings and record arrival times for P waves and S waves. An example is shown below. When we look at a seismogram, which shows the arrival times of seismic waves, we notice that the P wave arrival time is identified by a sudden disturbance within the seismogram reading. The first disturbance is the arrival time of the P wave. So we look for the very first, what I call a kick, where the seismogram will go up, and this is the initial arrival of that P wave at the seismograph station. So we record the time when this arrives. If we put an arrow straight down from the very first point where the P wave arrives, and we record that time, that is the arrival time of the very first P wave. So in this case, the arrival time of the P wave, we read it off the scale down below, would be 23 minutes. So the earthquake P wave occurred or arrived at the seismograph station at 23 minutes. Now we look at the second group of disturbances in the seismogram. This marks the arrival time of the S wave. So we look for a similar position that we recorded the P wave, and we record this from the S wave arrival time. So the very first kick of the S wave, and we put an arrow straight down to the actual scale, we'll see that the S wave arrived at 27 minutes. So the arrival of the P wave was recorded at 23 minutes, and the arrival of the S wave was recorded at 27 minutes. We use these 2 arrival times to calculate the difference in arrival time. So step 2, we record the difference in arrival times. To do this, we subtract the arrival time of the S wave from the arrival time of the P wave. And in this case, we have 27 minutes, which records the arrival time of the P wave, minus 23 minutes, which was the arrival time of the S wave, and we get a difference in arrival times between the 2 seismic waves of 4 minutes. Thus, the S wave arrived 4 minutes after the P wave. Next, you take this difference in arrival time, which is 4 minutes, and you plot it on the travel time graph. So when we put 4 minutes and we mark it off on the travel time graph, we notice here that the 4 minutes would indicate 4 blocks. So next we need to take the difference in arrival time, which is a line representing 4 blocks, and we slide it along the P wave. As we slide it along the P wave, 4 blocks will match up between the P wave arrival time and the S wave arrival time in one distinct spot. And if we look over to the right, represented by the red line, we notice that the difference in arrival time between the P wave and the S wave would be equal to 4 blocks, which represents 4 minutes. So we get 1 minute, 2 minutes, 3 minutes, 4 minutes. Once we determine the location between the P wave and the S wave, which corresponds to the difference in arrival time, and in this case 4 minutes, which represents 4 blocks in between the two lines, we then extend the line straight down and we can read off the distance from the scale below. So directly down beneath the position which represents a difference in arrival time of 4 minutes, we extend the arrow down and we read off the distance from the scale on the horizontal axis, and this corresponds to 2,500 kilometers. So the distance of this seismograph station from the actual epicenter of the earthquake will be a distance of 2,500 kilometers. As we noted before, we assume that we need 3 seismograph stations in order to determine the epicenter of an earthquake. So we assume that 2 other seismograph stations, if we do the exact same procedure as the first seismograph station, we could find out that seismograph station 2 is located 3,500 kilometers away from the earthquake epicenter, and seismograph station 3 is 4,500 kilometers away from the earthquake epicenter. So if we use these 3 distances, we can use a process called triangulation to pinpoint the epicenter of the earthquake. The distance to the epicenter from each seismograph station will be as follows. Station 1 was 2,500 kilometers away. Station 2 would be 3,500 kilometers away. And Station 4 would be 4,500 kilometers away. Using these 3 distances, at each seismograph station, we can draw a circle on a map that has the radius equal to the distance to the epicenter from each seismograph station. 3 such circles will intersect at one point, and this point would be the location of the epicenter of the earthquake. And the focus, which is the point of origin where the earthquake energy was released, will be directly below this point on Earth's surface. Therefore, the focus of the earthquake is located directly below where the 3 circles intersect. So if we look at the 3 circles, seismograph station 1 is represented here by a smaller circle, and the distance of the epicenter is 2,500 kilometers away. So all points on this circle from the epicenter Earth, or from the seismograph station number 1, will be 2,500 kilometers. If we look at seismograph station number 2, represented by the dot, and we draw a circle that's 3,500 kilometers away from that seismograph station, then all points on the second circle will be 3,500 kilometers away. And if we notice that this circle, the small circle, which is 2,500 kilometers, and the medium circle, which is 3,500 kilometers, intersect at 2 points. The first point here, and the second point right here. This is why we need a 3rd seismograph station reading. So when we draw the distance around the 3rd seismograph station, which is 4,500 kilometers away, that is all the distances from the seismograph station on this circle will be 4,500 kilometers away from the station. We notice that all 3 circles will cross in one point, and this is the point where the earthquake originated. Therefore, in summary, we need 3 seismograph stations in order to pinpoint the earthquake epicenter, and we'll notice that each of the 3 of the circles will cross at one given point, and that is the point at which the earthquake originated. Let's look at some examples. Example 1. It reads, if the distance of the earthquake from 2 seismograph stations to the epicenter is known, then the epicenter is A, midway between the 2 stations, B, at one of the 3 possible locations, C, at one of 2 possible locations, or D, beneath one of the stations. So, if we look here, we could draw 2 circles. And if we draw 2 circles, which represent 2 seismograph stations, seismograph station A and seismograph station B, we would notice that the 2 circles cross at 2 points. One point here on the left, and a second point here on the right. Therefore, the epicenter could be located at either of these 2 points, because the earthquake epicenter is a certain distance away from A, and all points on this circle will be the same distance from seismograph station A. And if we do the same with B, then all points on the circle surrounding B will be the same distance from seismograph station B. Therefore, the epicenter must be located at one of the 2 points where the circles overlap. So your answer in this question would be C. The epicenter would have to be in one of 2 possible locations, and that's where your circles overlap. If we look at the next question, next question reads, how many seismograph stations are needed to locate the position of an epicenter? So if you look at the question above, 2 seismograph stations will give a possibility of 2 different locations. Therefore, this is why we need a 3rd seismograph station, seismograph station C. And if we draw a circle around seismograph station C, we'll notice that all 3 circles cross at one given point, and that would be the location of your epicenter. So your epicenter will be located where all 3 circles intersect. So how many seismograph stations are needed in order to locate the exact position to pinpoint the epicenter of an earthquake? Your answer would be C. Let's look at another question. Example number 2 says, as a result of an earthquake, the seismogram below was obtained. What is the distance from the recording station to the epicenter? To investigate the distance of the recording station to the epicenter, we would first have to look at your seismogram and notice the arrival time of the P wave. The arrival time of the P wave, located here by the very first disturbance, and from this we can draw a line straight down and read off that value. And the time when that first P wave arrived was 23 minutes. Then we look for a second seismograph arrival time, which is the S wave. The very first disturbance, record that straight down and record that time, and in this case it'll be 27 minutes. So we need the arrival time of both the P wave and the S wave in order to determine the difference in arrival time. Once we find the difference in arrival times, and in this case it'll be 27 minus 23 minutes, which equals 4 minutes. Once we know that the difference in arrival time was 4 minutes, we then can go to a distance time graph and use 4 minutes. So 4 minutes time would represent 4 blocks. So if we look at the arrival time between the P wave line and the arrival time of the S-wave line, we need the difference in arrival times as 4 minutes, which equals 4 blocks. So if we look here at 2,000 kilometers away from the earthquake, you notice that the difference in arrival time, or the distance between the two lines, will be 1, 2, about 3 blocks. If you look at 3,000, we notice that the difference in arrival time will be 1, 2, 3, a little over 4 minutes. So if we go in between at 2,500 kilometers, we can record here, we get 1 block, 2 blocks, 3 blocks, 4 blocks. So the difference here would be approximately 4 minutes. So we draw an arrow straight down, and we can read off the distance at which the epicenter was away. In this case, it would be 2,500 kilometers. So the distance of the seismograph, the distance of the earthquake epicenter would be approximately 2,500 kilometers away. Let's look at the second part of this question. The second part says the second recording station located 3,500 kilometers from the epicenter recorded the P wave arrival time at 10 a.m. At what time did the S wave arrive at this station? So if we know at 3,500 kilometers, we know the distance that the epicenter is away, and we know that the P wave arrived at 10 a.m. at 3,500 kilometer station, then the S wave will be the second wave to arrive. So if we go to our diagram at 3,500 kilometers, which is right here in the middle, we can draw a line straight up where it intersects the P wave line. So we know that this P wave arrived at 10 a.m. If each block represents 1 minute, then we can count the number of blocks above and estimate the arrival time of the S wave. And in this case, we have 1, 2, 3, 4, 5 blocks. So the S wave arrived 5 minutes after the P wave. Therefore, the arrival time of the S wave would have been at 10 minutes, at 10:05, just 5 minutes after the arrival time of the S wave. So at 10:05 a.m. So 10:05 a.m. was the arrival time of the S wave. Your turn. Take the time now to read the following question and prepare your answer. And you can record or stop the recording now so you can prepare your answer. And the answer to the question will be on the following slide. The question reads, with reference to the graph, answer the next 2 questions. First question reads, if the difference between the first P wave and the first S wave is 10 minutes, how far away is the epicenter of the earthquake? So if we look at the question, we see that the first P wave and the first S wave was 10 minutes apart. So this will be your difference in arrival times. So if we can go over and look at the difference in arrival time, we need to match up 10 minutes between the P wave line and the S wave line. If we look at the answers at 3,000 kilometers away, if we could go up straight up from 3,000, we'll notice that the difference in arrival time was not even 1 full block. And 1 full block only represents 5 minutes. So therefore, 3,000 could not be your best answer. If we skip over to 6,000, we go up from 6,000 6,000 only is represented by approximately 1.5 blocks. So therefore, that would be about 7.5 minutes. So if we go over to the final choice D, which was 9,000 kilometers, we notice that choice D would be approximately 2 full blocks from the P wave to the S wave. 1 block, approximately 2 full blocks. Therefore, it would be 10 minutes, because 2 full blocks would represent 10 minutes in time. So your answer to this question would be D. Your earthquake epicenter would be approximately 9,000 kilometers away. The second question reads, if an earthquake is 5,000 kilometers from a seismic station, the first S wave would arrive at the station in how many minutes? So if we go to our question, we know that the distance to the seismograph station is 5,000. Now we want to know when the actual earthquake wave would arrive at the station. So if we go up from 5,000, so we know that's the distance, the P wave arrived at approximately 7 to 8 minutes. But if we keep going until we intersect with the S wave arrival time, we come across and we notice that the arrival time of the S wave was at 15 minutes. So our answer to this question would be D. The S wave arrived at approximately 15 minutes. So in summary, if we look at the overview of the points covered in this presentation, to find the location of an earthquake, we use a method called triangulation. In order to use triangulation, we need to get the distance of the epicenter from each seismograph station. And we need at least 3 seismograph station readings in order to find the epicenter. And once you have the readings from 3 seismograph stations, we can calculate the distance to the epicenter by using the following steps. First, calculate the difference in arrival time between the P and S wave. Once you know the difference in arrival time, we can use the travel time graph to find the distance of each station. Once we know the distance of each station, we can draw this distance on a map represented by 3 circles from each station. And the distance of the circle from the seismograph station will be the radius of the circle. And once you draw 3 circles, one around each of the 3 different seismograph stations, we will notice that each of the circles will cross in only one point. And this intersection of the 3 circles is the location of the epicenter. So these are the points that you use to find the epicenter of an earthquake.